Thank you for that amazing introduction, Tim GPT. So it's been about 2 years since I was at iOS conference SG here in Singapore, and 2 years ago I spoke about Swift concurrency, and it was pretty new back then, and I may have lied to you a little bit, I realized now. Because I was saying that Swift concurrency was such a beautiful, simple interface, and it was designed with the user in mind, and that it would be so easy to write a simple async function. I think we've all seen this. And I mentioned things like it's so beautiful that it does progressive disclosure. You can start with your async function and await them, and Swift won't yell at you about it. And then you use task groups and tasks and child. You go nuts with it. You go as far as you want to use actors. It's all fine. Swift loves it. And then you might have turned on strict concurrency or started looking at Swift 6, and then Swift started actually yelling at you for doing the simplest, stupidest things. It's telling you passing closure is a sending parameter risk causing data races between code in the current task and concurrent execution of the closure. And you're like, what? Okay, fine. Or maybe you see something like this, sending main actor isolated instance cell view model to non-isolated instance method load items. I'm just going to stop reading there. I'm not sending that view model anywhere, Swift. It's not going away. Non-sendable type movie returned by implicitly async. It's not implicit. I awaited it on purpose. I don't know what Swift is thinking, but Swift 6 is making my life harder, and probably your lives even harder. So yeah, Swift 6. Concurrency did make us a bunch of promises. Promises async await syntax, we have that. And it's pretty decent, it's pretty good. If you only use that, you're fine. It promises structured concurrency. That actually works pretty well. And it promises compile time data race protections, and that is the bane of everybody's existence that's trying to do Swift 6 at this point. So I took the liberty of breaking that part, data race protections, down into 3 main pillars. They're defined by me, made up about 24 hours ago or so, unofficial. ChatGPT doesn't even know. I wish it would have said that, like Donnie Walls, definer of the 3 pillars, but it didn't. So we have isolation, we have actors, and we have sendability. The 3 topics that I would love to talk about today. I think if you get these 3, you will understand the compiler errors. You still hate them. You still won't be able to solve them, but at least you'll be able to understand what the compiler is trying to tell you. Because the compiler has its own perspective on your code. You might have code that runs perfectly fine, and you know that it's free of data races. But the compiler reads it, and it goes, no, that's not free of data races. You go, yeah, but it is. No, you see, you could, in the future, if you wanted to, maybe, potentially, run these 2 things at the exact same time, and you have a data race. So we need to understand how the compiler looks at our code, and how we can tell the compiler when it's wrong, how we can nudge the compiler to understand us, and also sometimes we need to know the compiler's perspective so that we can know when to give up on Swift 6 and go back to strict concurrency checks and only have warnings. So actors, sendable, and isolation. Where do we even start? Over the past 2 or so months, I wrote this talk starting with isolation. I wrote this talk starting with sendable. I wrote it starting with actors, and then I realized, let's make a Venn diagram. It's basically a circle. Like, they're so closely related, but we have to start somewhere, and it's hard to talk about them in isolation. I know half the crowd can't see that, but that pun was absolutely intended. I decided to start with actors, and that's because actors sort of bring everything together. When I wrote the talk starting with isolation, most of my examples involved actors. When I want to talk about sendable, guess what I used as examples most? Actors. So I thought I'll explain them first, and then we sort of tack the rest on. And hopefully by the end you understand all 3 well enough to understand what the compiler is trying to tell you. So if we don't have actors, so we go back a little bit. How do we protect state? Like Christian's trying to do right now. Are you using that? Yeah. Did you try this? Yeah. Have you considered that one yet? Right, we can use locks to make sure that we gain exclusive access to resources, and we can let go of the lock to let the system gain other resources. We can use dispatch queue to put a bunch of work on a queue and make sure that only one thing at a time executes. We can use semaphores to limit access to a limited number of resources. And it works, right? These things are not available in Swift concurrency in the same capacity, but we have something before. However, it was completely up to us to make sure that we use these things correctly. I mean, I actually looked at Christian's code today, and he's using the things correctly as far as I could tell, but he has a data race. Only when he presses enter in SwiftUI. Can you imagine? He can type anything he wants. When he presses enter, boom. And it's notoriously hard to debug. I love that just this example happened today. And it's not hard to write unsafe code. Right? We can write code like this, an uploader with a private variable upload task. We can start uploads, append to a list. What's wrong with this? This will crash, probably. Maybe I need to add a little more uploads, but this could crash. The reason is, when I start an upload, I append to an array. When I do that twice at the same time, I'm appending to that array concurrently, which means I'm modifying memory in one address from two places, and that's a classic definition of a data race. So this would crash. If I'm lucky, I get this, pointing to a line of code somewhere in my uploader. If I'm unlucky, I'll get a crash log saying CF tag pointer, some sort of table view I've seen, dates I've seen come across. I'm like, I'm not using that anywhere, so what's actually wrong? It's almost impossible to figure out unless you start actively hunting for your data races. So writing that safe code is 100% your job. So when Apple announced that they were going to give us compile time data race safety, I think the time I was as happy with that was probably when they said, nil will no longer crash your app. Right? It didn't in Objective-C, but I also did some Java at some point, and in Java every other line is check that this is not null because otherwise things will crash. In Swift, you could actually encode that this thing might be nil or not, and it's very explicit. It eliminated a whole class of bugs. And compile time data race protections would do the same thing for us. And actors actually have this built in. Right? Actors make sure that we don't have data races because the compiler will help us, the actor will make sure that everything is synchronized, and it's all really nice. So when I talk about actors, there's a couple of terms that I use that we're going to look at today. We're going to look at something called the actor mailbox, actor reentrancy, and actor isolation. Reentrancy I'm going to mostly skip over for today. That's because I could probably do a whole talk on that alone. What it essentially means is that if an actor is asynchronously waiting for something to come back, the actor is going to go ahead and do something else. I'll elaborate on that when we talk about the mailbox, because you can't understand reentrancy if you don't also talk a bit about mailbox. Anyway, consider this date formatter cache. It's very similar to that uploader we saw before. It's got a private dictionary. I have a function for format string, returns a date formatter. If we have one in the cache, great, we return it. If we don't, we make a new one, configure it, cache it, and return it. If we use that, concurrently this crashes, of course, but if we use it normally, most of our code would look like this. We ask the formatter cache for an instance, we get it back, and we can print dates. It's beautiful. Simple and convenient, but unsafe. So let's say that we go ahead and fix that. All we need to do is this. We can change a single keyword, go from a class to an actor, boom, we have safety. It's super simple, super nice. The problem isn't this. The problem isn't the definition of this actor. The problem is that usage now becomes more complex, because if I have that exact same code, the compiler is now going to tell me that a call to an actor-isolated instance method formatter cache in a synchronous, non-isolated context, and that I have to await that because it's implicitly asynchronous. So when you're interacting with an actor from outside of the actor, calling methods or accessing state is implicitly, I put that in parentheses because it's not that implicit, but you didn't make the thing async, and it became async, so it's somewhat implicit. But you're not in the actor, so you have to wait your turn. Because we're now in Swift concurrencies world. So if I want to interact with this actor, I have to await cache instance formatter. You can see I had to wrap this in a task. So I'm now introducing concurrency where maybe I didn't even want it in the first place. So why is that needed? Well, that's where the actor mailbox comes in. An actor only does one thing at a time. Right? I want you to keep that in mind. An actor always only does one thing at a time. So what happens is the actor has a so-called mailbox, and we put function calls, property access, anything we want to do, into that mailbox. The first thing that goes in, the actor sees that, it's eager to do work. It goes, okay, I'll get that formatter for you. In the meantime, other things concurrently start asking for it, and the actor just, at its own pace, starts going through this. Now, I mentioned reentrancy. What happens with reentrancy is the actor does one thing at a time. Once it starts to wait for something, like a network call, an actor loves to do work. So it goes, okay, this network call is busy. I'll just pick up the next task in the meantime until that comes back. So it does one thing at a time, but not atomically. Just so you know what reentrancy sort of is as a problem. Not the point of this talk. The point is, when you introduce actors, you introduce concurrency. Because we have to await whatever we put into that mailbox. So if we want to ask for a formatter, the actor might be doing something else at that time, so we have to wait for it. Let's talk a little bit about isolation, because this is all about isolation. In this case, I have a small actor token manager as one property, current user. What we say is that current user is isolated to the actor manager, to the token manager. And because it's isolated to the token manager, when we want to get it out, we have to wait for it. So right here, in my networking object, which is not isolated to anything, it's just a plain class, we call that non-isolated, it creates that manager. Let manager equals token manager current user. Code should be fine, it's not. You get an error here saying sending user risks causing data races. Sending user to actor isolated initializer in its current user risks causing data races between actor isolated and local non-isolated users. This already tells us a lot about isolation, because it is indeed saying current user and the initializer are both isolated to the actor token manager, which means that if the token manager owns that current user instance, it wants to exclusively own it. It wants to isolate it. It wants to make sure that nobody does anything weird to it. But our networking class also has a reference to it. So at this point, our non-isolated networking object and our isolated token manager both have access to user. Now, we'll talk about sendable later, but user is not sendable. This means that user is not safe to use in two isolation contexts at the same time. All right? So that's what sending user to actor isolated initializer means. We take it from a non-isolated place, sending it to a place that is isolated. These two are not friends. So in Swift concurrency, your code is always going to be either isolated to an actor or non-isolated. There's nothing in between. Either isolated to an actor or you're not. Objects and state that exist within the same isolation context can be accessed freely. This means that an actor can access its own methods without awaiting it. It's in the same isolation context. An actor can access its own state without awaiting it. Same isolation context. Also, an actor is allowed to mutate its own state. Same isolation context. When you pass objects or state between isolation contexts, that is only allowed under certain conditions, because that's where the compiler goes, hold on, if two isolation contexts are able to access this piece of state at the same time, that might be a data race. We don't know what any of these isolation contexts will do with it, but they might be doing something bad. So the token manager has its own isolation context, and networking is non-isolated. So when we pass current user from networking to our actor, we cross what's called an isolation boundary. There are several ways that an object can be isolated. We've already seen actors. Actors have their own isolation context. You can also use global actors to isolate arbitrary objects, methods, and state to a shared actor instance. This is the main actor, for example. You've probably seen @main actor added to a class, or to a function, or to a piece of state. That's what a global actor is, and that isolates that piece of state to one single main actor instance. It means that two unrelated objects can live in the same isolation context, and they can talk to each other. They're friends. A task inherits its current isolation context. So whenever I make a new task, if I make that task from a main actor isolated context, that task also lives in the main actor context. So let's look at an example of using a global actor. If I have this code right here, an observable list view model with a bunch of items in it, and a load item async function, and a view model inside of a view, I get an error that looks like this. Sending main actor isolated self view model to non-isolated instance method load items risks causing data races between non-isolated and main actor isolated users. It's a variation of the error you saw before. The first time I read this, I looked at it, and I, out loud, said to the compiler, excuse me? Sending main actor isolated instance self view model. I'm not sending it anywhere. Maybe into the task, but okay, I'll work with that. I'm sending it into the task. Fine. Okay, not to the task, apparently. Two non-isolated method load items. I'm not doing that. The view model is staying where it was before. It's staying inside of the view. So what are we talking about here? It risks data races between non-isolated and main actor isolated views. Who thinks they have an idea of what this actually means? Mr. Functional, obviously. So what it means is this view is main actor isolated. That's because the view protocol gained a main actor annotation, so it is isolated to main. We get that. The task I create inherits isolation context, so that task also runs on main. So that's not my problem. Inside of the task, I have access to the view model, which is fine. The task and the view model are main actor isolated. So in that part, we're good. Load items is defined on a non-isolated class. It's a non-isolated async function. It has access to self. What does self point to? The exact same instance of view model as I have in my view. So that does mean that I have access to that one instance from a non-isolated context inside of my view model, and I have access in the isolated context inside of my task. Okay, cool. Switch UI views are all isolated to the main actor. View model instance, therefore, is also isolated to the main actor. We call non-isolated async method on the view model. It's accessed from the main actor and itself. So we know what's wrong. How do we fix that? We could make sure that the view's access is also non-isolated. Even if we could, I don't think we can. It sounds like it's a terrible idea. We could make the view model safe to be passed across isolation boundaries. That works, but once you understand how sendable works, that becomes kind of a problem because we have mutable states, so that's not an option. Or we could isolate the view model to the same actor as the view. That's not such a bad idea. We could apply a main actor annotation to our view model, and now that view model also is isolated. So items is isolated, load items is isolated. They're both isolated to the main actor, just like the view. So now we can freely access self and the view model at the same time without problems, because we're all living in the main actor now. Do note that if you have an asynchronous operation inside of load items, like maybe you're awaiting a network call, that doesn't block the main actor. I think it's important to call that out. Awaiting something does never block the current actor. In fact, it allows the current actor to go ahead and be reentrant, like we talked about in actor reentrancy, and go do something else so that it keeps itself busy and the network call actually is run somewhere else. So that's not a problem. With a global actor, you limit isolation contexts, which is good. You want to have as few of them as possible because it just makes your program simpler. And it allows you to reduce concurrency. And coincidentally, reducing concurrency is precisely what the Apple team is currently, like the Swift team, is currently looking into. They basically realized, and they have a proposal up, that they're having us introduce so much concurrency into our app, a lot more than we probably want. So they're thinking about ways in which we can either automatically isolate things to the main actor if we call them from main, or possibly even making your apps mainly main actor by default, where you must explicitly leave. So reducing concurrency, Apple's thinking about it. It's probably a good thing to do that. However, you might have multiple isolation boundaries, and you could actually have state that's unsafe safely cross over. Do you remember this? We saw that a little bit earlier, like 2 minutes ago. I hope you remember, otherwise short-term memory is... So if we pass that current user, it's actually a bit more than 2 minutes. My memory might be bad. So that user is passed from the class networking, which is non-isolated, into our actor, which is isolated. So that's not allowed, because that user now lives in two isolation contexts, and that user, like I said, was not safe to be passed across isolation boundaries. However, this code is fine. I'm creating an instance of user inside of my non-isolated create manager function, so that user is definitely not isolated to anything. And I'm passing it into my token manager. The compiler accepts this since Swift 6. And that's a Swift 6 compiler, not the language mode. So you can have the Swift 5 language mode, Swift 6 compiler, and use this. This is a feature called region-based isolation. And with region-based isolation, the compiler can see that our user starts off in a create manager's isolation context, which is, in this case, non-isolated. It can then see that we pass it to the token manager's isolation context, which is a new one. So it's now transferred from A to B. And it also sees that we never use it again. So basically, the compiler says, okay, you created this in A. It's technically not safe to go to B, but if A never touches it again, I'll allow it. So the compiler knows that this is okay, because user is only ever used in one isolation context at a time. Have you ever tried to do this in Swift 5? It's pretty much the same thing as we had before. And if you have, then the compiler would tell you something about capturing non-sendable state in a sendable closure. But the pattern looks familiar, doesn't it? It's pretty much the same thing. So you would hope that region-based isolation that we had here would also apply in the case of a task here. Sadly, it doesn't. In Swift 5, task took a sendable closure. So that's slightly different from being able to apply region-based isolation. If I mimic this and I define a variable that is a sendable closure and I capture a user in there, I get my error. Capture of user with non-sendable type user in a sendable closure when compiled with Swift 6. However, in Swift 6, we are allowed to do this with tasks, and they made some changes to task continuations and more. But to get that, we're going to move into our final pillar of concurrency, and that is sendable. So hold that thought on why we are allowed to cross isolation boundaries with tasks now. When an object is sendable, we know that it is safe to be used concurrently. We know that it is allowed to cross isolation boundaries. We know that no matter what we do with it, no matter how concurrent we are with that object, it should never have a data race. The object can be passed across isolation boundaries without problems, and multiple isolation boundaries can hold a reference to that object. And the compiler will enforce this for us. Right? If something isn't sendable, the compiler will tell us, hey, you're doing something with this object, and it's only allowed if that object were sendable. The cool thing is actors are always sendable because of their own isolation context, because of them protecting their state from data races. So that's nice. Other objects can also be sendable. A struct, for example, is sendable if all of its members are sendable. It conforms to the sendable protocol, which you don't have to do explicitly if the struct is internal. Only public structs must be explicitly made sendable. And that's actually a really good thing, because if you have a public struct that just by accident happens to be sendable, you don't want that to suddenly be part of your public API contract, because now you're stuck making that struct sendable forever, and that might never have been your intention. So, a sendable struct, an example. Class user, completely not sendable. Our first struct right here, it has a let ID of type UUID. UUID is sendable. And a var count of type int. Int is sendable. The fact that we have mutable state on this struct is completely fine. If we pass this struct from one isolation context to the next, each one has its own copy, so making changes to the count does not impact the other copy. We're fine. The second struct has only let properties, but it has a reference type user, which is not sendable as one of its members. So the compiler is going to tell you that is not sendable. Enums are sendable if they have no associated values. If you just have an enum with a list of cases, that's fine, that's sendable. If you do have associated values, those associated values must be sendable themselves. And you must conform it to sendable. So in example again, the top enum is safe. It has an associated value on its user case of sendable struct. Name implies that's sendable, so we're good. The second one has a case user with the class user, which was not sendable, so the compiler is going to tell us that is not okay. Classes are a special creature. They can be sendable if all of their members are sendable. We're kind of used to that by now. They can't have any mutable state because they're reference types. So if we pass them to two isolation boundaries and both can be mutating a var, then we might have a data race. So we can only have lets on our sendable class. The class must be final, so we can't be inherited from anymore. This is the end of the line. And we must conform it to sendable by hand. If we meet all these criteria, the class can be sendable. So, example time, top class is sendable, two let properties, UUID int, we're good. Bottom one, two let properties, but one of them is user, so we're not good. But what if my class is thread safe? Because I'm refactoring my code, I know that this class is completely thread safe. I did everything I could. I used logs, dispatch queues, semaphores, everything. It's fine. I have tests. I listened to Christoph. But it doesn't apply. Like, it has vars. I can use unchecked sendable. So you can make anything you want sendable with this, and you should totally do it. No, don't do it. It makes sense to use it sometimes. If you know that the class is thread safe and you have to test to prove it, and you intend to revisit and adjust your class at a later time, And really, you should only use it temporary. It makes full sense, in my opinion, to do this while you're refactoring. You can't refactor every object at the same time. But this should not stick in your code base for a really long time. So that's types. We also have sendable closure. And a sendable closure is safe to run from any isolation context concurrently, as you might imagine. And that means that it's only allowed to capture sendable state. Do you see where we're going with that one? We had the variable in the beginning with the sendable closure, and it captured some states. If we define or accept a sendable closure, we can do this. Var my closure is of type sendable function that takes no arguments, is async, throws, and returns void. Or we can have a function that takes an argument of the same type. A sendable closure can be async, it can be throwing, it can be both, or it can be neither. Okay, so functions can take async throwing sendable closures, or they can take plain sendable closures. But in a lot of situations, a sendable closure, if you're writing an API that takes a closure that you want to run in a different isolation context, a sendable closure is probably not what you intend to receive. Because, as we sort of discussed earlier, this code is technically safe. I'm creating an instance of user, passing it into a sendable closure, but the compiler won't let me do that because user is not sendable. To fix that, the Swift 6 introduces sending. Sending is a new keyword, as if we hadn't enough keywords in Swift. So we have another one, sending, and we can now pass a user instance that we created inside of our function into a sending closure. And this is very similar to region-based isolation in the sense that the compiler is going to make sure that this user that we pass from one isolation context into that closure is never used after we send it. Right, so let's explore that a little bit. Tasks now take sending closures. Continuations use sending closures, and task groups use sending closures. So that's the case since Swift 6, and that's why you could pass a non-sendable user into a task now. And probably if you have closures that take sendable, functions that take sendable closures, you should try and make them sending. It's simply a little bit more convenient to work with from the call side. And it's just as safe. Because the compiler helps us here. In this case, we would get an error. Because I have my let user, I pass it to a sendable closure, and then I try to print its name. The compiler is going to tell me, no, you can't do that, because value of non-sendable type, colleague guaranteed, void returns nothing, accessed after being transferred later, access could raise. Best compiler error ever. Luckily, this is on the lines where you're using it, and especially that last one, access can happen concurrently. That should tell you, hold on a second, I'm doing something that is sending, and that's not okay. So the compiler now knows that run sendable example and that last print could actually run concurrently, and that might be a problem. So the next time you see something like this, sending closure as a sending parameter risks causing data races between code in the current task and concurrent execution of the closure. You know, this is probably related to the fact that I'm using user inside of my task and outside of my task. The user got captured in the task, probably was an instance member, so it wasn't allowed anyway. But now you know that that's probably related to that. Or if you see sending main actor isolated self view model to non-isolated instance method load items, you now know that view model belongs to the main actor, load items is non-isolated, but it has access to self. So now your view model is accessed from the main actor and the non-isolated context. And that's the problem. And you know that your view models might need to be main actor annotated. Or if you see this one, non-sendable type movie returned by implicitly asynchronous call to non-isolated function cannot cross actor boundary. You now know that that function is main actor isolated, load movies is async and non-isolated, movie is not sendable but it's created in a non-isolated context, you send it to something that's isolated, hey, that's not okay. How do I solve it? Well, that's a different problem. At least you understand why you have the problem. Or if you see this, static property shared is not concurrency safe because non-sendable type date formatter cache may have shared mutable state. You now know that apparently you're doing something that isn't sendable. Maybe that date formatter cache should be sendable. Maybe you should make it an actor. So how do you deal with all these compiler errors? First of all, if you see a compiler error related to sending something or something passing isolation boundaries, ask yourself whether you intended to introduce concurrency. When your view model tells you that you're doing something that isn't isolated and you now have a concurrency problem, you probably never intended for that function to be async. Mark it main actor. It's completely fine. If you're not sure about that, try to trace something that doesn't use concurrency. Put some thread is main all the way from your view to your networking code. I'm willing to bet that in most cases, you don't leave the main actor until right before you make the network call. So you're probably okay with the main actor in a lot of places. And then figure out the smallest change that makes sense. Don't refactor everything. The more you refactor, the more problems you might probably introduce. And then think really hard about your intentions again. Did you really want concurrency here? Really, don't be afraid to run that app code on the main actor. It's probably where it belongs. Apple wants it to be the default, probably, most likely, is what they seem to be leaning into. And also, don't make everything an actor. Like, it might be tempting at some point to go, you know what, I'm going to embrace concurrency all the way. Everything's an actor now. Just let's go. And again, just to drive that home, try and reduce concurrency rather than increase it. It is a tool to be used when it makes sense. Not everything in your app should be concurrent. Thank you very much.